What are self-adjoint matrices? In the real case, these are symmetric. In the complex case, it is Hermitian. Right? So this theorem says that whether you have a symmetric real matrix or a Hermitian complex matrix, whenever you have two different eigenvalues, they will be orthogonal. Okay, it's kind of interesting. So, proof. Let A be the eigenvalue of a matrix A. Again, this is self-adjoint with eigenvector U, and B be the eigenvalue sorry, I don't like this. Let me try again. Right, I'm writing too much. I want to be compact so that you don't have to write too much on it. Let me try this again. Okay, proof. Let A, B be eigenvalues of A, which is self-adjoint, with eigenvectors U, V, respectively. Yeah, so I can write less by doing this. So I'm saying that A is the eigenvector for U, and B is the eigenvector for V. So in other words, i.e., in other words, A times U is AU, and A times V is equal to BV. Suppose A is not equal to B. Right? So it's our assumption. So you have two eigenvectors U and V whose eigenvalues are different. Now let's see what happens if you have such a case. Right? So we can say AUV can be computed in two different ways. One is AUV would be, what can you replace AU by? AU is small AU, and then V, and then A comes out, right? So it's A times UV. Okay? Now, instead of this, you can do the adjoint, right? How do you use the adjoint? If you want to move a matrix to the second component, second place, you use the adjoint. Right? So it's equal to U adjoint of A, V. But that because A is self-adjoint, it's the same as U, A, V. Okay? And then what do we know? AV is BV, right? Small b, v. That's what we have over here, right? And then, if it's a real inner product, then B just comes out. Nothing has to be done. But if it's a complex one, what do? B comes out as what? You have to do complex conjugate. Yeah, so B comes out as complex conjugate. But wait. We know something about A and B. These are eigenvalues of a Hermitian matrix. We know something about it.
They're not equal.
No, that's our assumption. But in general, if you have a Hermitian matrix and you have an eigenvalue, we proved something about it. What did we prove about it? That it must be
Real.
real. Right? So b has to be a real value. So what is b bar? Complex conjugate of a real number is itself. So now, what did we just prove? We proved that a uv is same as b uv. Move everything to this other side and you get a uv minus b uv equal to 0. And you can further factor the uv out because this is just a number, right? It's some number multiplied. So you factor it out and you get a minus a times uv equal to 0. Oh wait, can a minus b equal to 0? A minus b equals to 0? No, because a and b are different, right? So you can divide both sides by a non-zero thing. There's no harm in that, right? There's always a problem when you divide by 0, so that's illegal. But since we know that a and b are different, I can divide both sides by a minus b and conclude that uv is equal to what?
0.
0. What does that mean?
Like orthogonal from each other?
They're perpendicular. Yeah. Okay? They're perpendicular. Yes.
So because we proved that they're perpendicular to each other, we show that a and b are not equal to each other?
No. If a and b are not equal to each other, then they're perpendicular to each other. Let me read through. Yeah.
Would you be able to do the same proof with the outer product?
No, outer product gives you a vector, so it's very different.
Oh, okay.
Yeah. Inner products are defined for any vector space. Outer products are only defined for dimension 3. Yeah, so yes. Cross products are nice when you're doing electromagnetics, but then once you get out of it, then you don't use it. You go to higher dimensions, you can't use it. This has actually far-reaching consequences as well because, I mean, when we solve differential equations, partial differential equations, we had this Sturm-Liouville problem. And Sturm-Liouville operators are actually self-adjoint with respect to some kind of an inner product on this function space. And that tells you that every eigenvectors of the Sturm-Liouville operator are orthogonal. And that gives rise to, like, if you have once you have that, then you have an orthogonal basis that can allow you to do all kinds of calculations. And that is really what gives you the cosine series and sine series in the PDEs when you solved it. So it has all these relationships, but if I were to take time to explain all that, it's going to take too much time. So, but this is still very important, so I still want you to know this.